Hello students, welcome back. Let's continue working on power series method. Previously we did a problem that was rather trivial, this problem. And the power series method was clearly an overkilling there. This is an equation with constant coefficient, so there is absolutely no reason for that. This one on the other hand will make some more sense. Ready? Okay, let's begin. As always, we take excuse me. Let's begin with finding the interval of convergence. Let's do that first. Okay, previously we didn't have to do it because it turned out the interval of convergence was infinity. But in this case, yeah, okay. We have some denominator here. Denominator is 1 plus t squared, and that becomes 0 as singularities I and negative I. And I'm going to take the expansion around t equals to 0. So t0 is 0. So the distance between 0 and I is going to be 1. So the interval of convergence is going to be given by this radius of convergence. Okay, all right. So we found out the radius of convergence and the interval of convergence first. Yeah, it's a good idea to do it first because after all those, you may end up forgetting it. You see, if you have something more complicated first and then easy one later, then you may end up forgetting the easier one after doing something really complicated and get exhausted. So it's a good idea to start with radius of convergence. Okay, we did it. Next, the standard. The original, derivative, and the second derivative. Any question here? Original, Cn, Tn, and then the derivative term by term, and the second derivative term by term. Any question here? It's always the case. Next, we have this ODE. Let's put some space in between. And then this one is going to be the red series. And this is the blue series. And then this one, I'm going to keep the same. Okay, and never mind. Let me put another color there, green. Okay, all right. Is everybody happy with this substitution? Okay, the series computation begins here. Let's see, we have the parentheses to break up. So let's go ahead and do that. I mean, I use those colors to get those association. I already did it, so I don't need any color anymore. So let me remove the colors and then let's break up the first series. Let's put some space in between. Okay, and then this one for t squared, and this is for just 1. Let's see, did I break up correctly here? 1 times this series, t squared times that series. So we have this and that. Looking okay. All right, next, let's take care of this t squared and this t. This one's all set, no problem there. This squares multiply, what do you get? We lose that minus 2. How about this? T power multiply by this, we lose this minus 1. And then let's use color coding here. This is blue and that's red. that's blue, and that's red. And I don't have any association with the previous anymore. Okay, just compare the color. T squared going up, becoming like this. T going up like this. Do you see the association? Are they the same? All okay? All right. Let's assume everybody understood. So I don't need this coloring anymore because everybody understood already. Okay, all right. Now I have to take all those powers together, and this one looks okay, t to the nth power. This too looks okay, t to the nth power. That's okay too, t to the nth power. This one doesn't look good, n minus second power. It needs some work. Are you with me here? This one doesn't look good. It needs some work. And I have to make it into t to the nth power, right? What method do I use? The index shifting. In the end, I have to get nth power. And how am I going to get nth power in the end? By starting from n plus 2. If I do that, I just highlighted in, I already used green, so let me use some other color. If I do this, then I'm going to get nth power here. So the key is t to the nth power. So that's where everything begins. And then now that I used n by n plus 2 substitution here, we'll have to do the same thing everywhere else. Here, I need n plus 2. And here, I'm going to need n plus 2. And here, I'm going to do n plus 2. And then n plus 2 here as well. Did I get everything here? All the substitutions? Please check. Did I get everything? Okay, assuming I got everything all right, let's move on. So n plus 2 equals to 2, so I can start from n equals to 0. That's a simplification. And this is n plus 2, that's fine. And this is n plus 2 minus 1, so n plus 1. And then this one, n plus 2, all right? And this is going to be nth power. Looks okay to me. So that's going to go here. So the index shifting gave me this. So this is going to go from n0, and this is going to be n plus 2, oops, wrong key, n plus 1, and then cn plus 2, and then nth power. So from this index shifting, we can see this step we got before becoming that. Is everybody with me here? Let's have a brief recap. As for finding the radius of convergence first, yes, if you keep something simple for the end, you may forget it, so it's better to start with it. All right, that's an easy one. Next, let's actually apply the power series method. Original, first derivative, second derivative. Always the starting point is like this. And then the original ODE. And then y double prime red, y prime blue, and y green. We end up with this equation. And then some straightforward algebra. Break up the parentheses, okay, times 1 and times t squared. And then multiply this t squared inward, multiply by t inward, so that we get t to the nth power, t to the nth power. Those two are all set. And this one, we started from that, so that 2 is all set. This one requires some more work because we don't have t to the nth power anymore here. So I'd have to do some index shifting. Okay, index shifting, that's always tricky. We replace n by n plus 2 to get there. And once you do that, replace that one in place of that green, which I did here. Now everything is t to the nth power. Everything is t to the nth power. Looks like we are ready. So what do we have here? N plus 2, n plus 1, c, n plus 2. Oh, excuse me, wrong key. And then next, n minus l, cn plus 4n c, excuse me, 4n cn plus 2cn. Okay, did I get everything right? I want the summation t to the nth power and everything in the middle. There's a bit of a problem here. This one begins from 0, that one begins from 2, that one begins from 1, that one begins from 0. So we need some work here at the starting point, but I claim this is going to be okay. Why is this going to be okay? Now I don't need this color anymore. Pay attention to this, which I'm highlighting red, and then made it into 0. Pay attention to this, I just highlighted in blue, and then made it into starting from 0. I just artificially changed from starting from n equals to 2 to n equals to 0, starting from n equals to 1 to n equals to 0. Is this justifiable? The answer is yes, because when n equals to 0, this is 0 times something, so adding 0, that doesn't change anything. Next, n equals to 1, 1 minus 1, this is 0, so again adding 0, so that didn't change anything either. Here, when n equals to 0, this is 0, so adding 0, so that didn't change anything. So potentially they were a bit of a problem, but in the end, didn't cause any trouble, and we got that. And by the way, that's going to be a feature of the ordinary point. If you do it in a singular point, no way. We have some further further complication here. So what do we have? We're gonna just set this inside equal to 0. And then we can solve for n plus 2, and you're gonna get a recursion. In the end, no, this is what we're gonna get. And some simplification. Some further algebra, oh my. Simplification. Let's see, what did I do here? I'll take all these inside OK together like this, and then simplify, and simplify further. Turns out n plus 1 is common, n plus 2 is also common. You can ask, Cn plus 2 is negative Cn. In the end, it became amazingly simple. So we started like this, and turned out it became amazingly simple in the end by some algebraic manipulation. And then, because we have something this simple, we can find out all those Cn's. So let's see. The recursive relation we got is Cn plus 2 is negative Cn. So if I start from n equal to 0, you're going to get this. 0 plus 2. And then we get C4, we get C6, and so on. And then if I start from C1, you're going to get all these. C3, C5, C7, and so on. We're going to get all these. So in general, we have negative 1 to the nth power C0, so we get this. But in general, in many cases, we are not going to get this simple expression like this, and probably you're going to end up with some numbers and dot, 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 and then leave it as just power series expansion expression. That's about it. But in this particular case, it was possible. Same for the odd case, like that. And this is the interval of convergence. Do you recognize the functions? What do you think? Alternating sign, some odd powers, even powers. It's a sort of geometric series. Turns out this geometric series and that geometric series. Oh, here's Mathematicus checking. Yes, they turn out to be right. Let's see, let's have a brief recap. Let me erase what I added here. Okay, that's the interval of convergence, no big deal. So original first derivative, second derivative, original ODE, after plugging in we get that. And then some algebraic manipulation, breaking up, and then multiplying the powers in, we get that. And this one requires index shifting. We did the index shifting as highlighted in purple, so we get t to the nth power everywhere. How did he do it is here. And then taking those like terms together, t to the nth power part is common. Oh, before that we took care of starting from n equal to 0, which you don't usually have to worry about for ordinary points, to tell the truth, because this is always the case. And then take those like terms together, we get the coefficient part. That's always equal to 0, we get that. And then some magical simplification, which I didn't see coming. Consequently, we get all these.